welcome back to a restart of the Introduction to Programming. This is probably gonna be a yearly theme. We're gonna restart the entire series to introduce new people into programming, since if you've watched the whole thing once, there isn't really a point to watch it again. Hopefully this will keep things up to date and I can correct mistakes I make in past years, in this case 1 year. And we're also gonna experiment with the schedule a bit. Times are gonna change a bit more, I guess. So far, Sunday afternoons to evenings have been working out decently well, but I'm not sure this is the most comfortable for me. In any case, we're going back to the very beginning of learning to program. Computers are incredible machines that we use in our day-to-day lives. And if you were to open up the hardware, the actual computer, the chips on them, they get incredibly complex. All in the name of performance, getting them faster, more efficient, getting them to do more stuff in less time, on less space. But the fundamental principle by which almost every single chip out there works, at least the normal ones, is rather simple. And so in a way, computers are simple. They're actually simple in two ways. One, in that the operation of a computer, in terms of understanding, is rather simple, even though the hardware can get a bit more complex, depending on what you actually want to do and achieve with your computer. The more capable it's supposed to be, the more complex the hardware will end up being. But they're also simple in the sense that they're rather dumb, if you can say that about a machine. Computers do exactly what you tell them to, and only what you tell them to. They take it 100% literal. You cannot give them a vague instruction and expect they solve it on their own. You have to give them specific instructions on how to do that. But maybe we're going a bit too fast here. Let's go back to what a computer actually does internally. What is a computer? How does it actually operate? How does it work? That's not supposed to be here. Why is that happening? That's better. Now I can see the... yeah, it's live. Alright. The main focus on our computer will be the memory, which is the part of the computer that can store information, that keeps track of things. And that's also gonna contain all the programs. It's also gonna contain all the stuff the programs work with and produce. It's also gonna be the interface where you can interact with the program. It's all just memory. And memory in a computer works with ones and zeros, binary. On, off, or low voltage, high voltage, two different unique states. Let's write down just a random number in binary. Or maybe not necessarily number, just some random string of zeros and ones. Just 6 different letters, numbers right now, digits. Could mean a lot of things. Doesn't really matter. Let's say this entire thing, 6 digits, is supposed to mean one specific thing. And then I have another, maybe just 5 digits. This is supposed to be another thing. Again, we don't know what. Could be anything. But this is supposed to mean it's supposed to mean something else. Maybe one last thing. This is also something unique, we don't know what. It's a third thing. And this could also be stored somewhere in memory. Now, writing this down in this way is something we can easily do because I'm just scribbling on an electronic piece of paper. A computer doesn't have the luxury. A computer knows ones and zeros, which we have, ones and zeros. And then you forget that, oh, we also have blank space in here. We separate these three different strings, combinations of ones and zeros, with a third state, the empty space in between. Computer doesn't have that. So the computer might have this in memory. And nothing else. And you might see the problem now. We can't really identify where one thing starts and the other ends. Like, I know from context right now, because I defined those numbers, that this is where one starts and stops, and this as well. Here's where it starts, here's where the third one ends. But that's something I know, but the computer doesn't know that. These separators don't exist in memory, just all ones and zeros. That would be rather useless, but we can work with that. So computers do have these separators after all, but they don't separate individual things. They separate predefined chunks of the memory, which we call memory cells. So if this entire thing would be one large piece of memory, like your entire computer memory that's available, the RAM, or maybe a USB stick, the flash drive, maybe your hard drive, just something the computer can use to store data, and this entire thing would be the full memory. We can spread this into chunks, and how big these chunks are is up to you in the end. But one common thing to do is organize them in groups of 8. It's 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 5, 6, 7. Oh, we're one short. Well, we spread it in groups of 8, so we have to add another 0 here. Could be also 1, but we're gonna fill the gap with a 0. And now we have 3 individual chunks in memory, which are 3 separate memory cells, which all hold one thing. And if I have something like this up here, which requires more space than available in one memory cell, we just have to combine it in 2. So if I want to have this format with 8 individual digits per chunk, but want to store all of these things above, well, I could fill in the gaps with a 0 and then 1, 0, 0, 0, 1, 0. The first thing is in the first memory cell, and then we use the second cell for the second thing, and again we have 5 in here, we need 8, we're just gonna fill in the rest with zeros. 0, 0, 0, 1, 1. And for the last one, we need 2 memory cells, because there's not enough space. We fill in 1 blank, this time we fill it in front, and then 1, 1, 1, 1, 1, 6, 7, 8. I've miscounted, I think. Yeah, I've miscounted quite a bit. So we don't need just 1 spacer here, we need 1, 2, 4. That's better. 1, 2, 4. 1001, 1000. That's better. So to get these three things, we have one memory cell here for the first, one memory cell here for the second, and two memory cells for the third. And by organizing it in chunks, the computer can now somewhat understand the difference between different things. To a degree. If you just look at the memory as is, you wouldn't know what memory cells are combined and which are left on their own. We know these two cells belong together. We also know that this and this cell are two separate things. But if you just were to present me this entire list of memory cells, I wouldn't have any idea. So this combining different memory cells and keeping them separate is something you will do as a programmer. You will tell the computer that information. And how that might work is a topic for quite a bit later. Just keep in mind that we always have to organize our data into individual chunks, which sometimes can be one single chunk, and for more advanced or bigger stuff, we need to combine several chunks together. And to use these chunks, we can now give them a number, an address, like a house address, so we know where we can find each thing. And we don't give numbers to every single digit, we only give the numbers to the chunks, which is much easier to work with, considering how big memory can be these days. So this could be 1, this could be 2, this could be 3, and this could be 4. Just count up a number, that's the easiest way. That way we have a unique number for each position, for each memory cell, and we can also conveniently calculate where the next piece of information would be. For example, tell someone that memory cell 3 is where a thing starts, and this thing is 2 cells large. So I could just go to 3. I know this is the first part of our thing. And we know it's 2 cells large, so we also have to include cell 4. 3 plus 1, the next cell over. And that's gonna be the rest of our thing. It's a very convenient way to handle memory. It's very easy to understand. We have addresses that each point to a specific chunk in memory. And sometimes we combine memory, sometimes we leave it on its own. Now here we started at address 1, which to a human makes sense. We start counting with 1. This is 1 memory cell, 2, 3, 4. In computer science, this is rather unusual. We don't start with a 1. We always work with zeros and ones in memory to represent different things. And so we would also use zeros and ones, binary, to represent these different addresses. So let me demonstrate. This would be in binary this, this, and this, and this. These would be the binary representations for these different addresses. So we need 2 digits to represent these 3 states, and for the 4th one we need 3 digits. That's kind of wasteful. There's still one other state we could represent with just 2 digits we didn't use. 0, 0. And then we could make this 0, 1, 1, 0, and this 1, 1. Now we used all different variations of just 2 digits. Each represents one address. Only now they don't represent 1 through 4. This is 0, 1, 2, 3. So what we do is start counting at 0. And we do that a lot. And there are other things we can do when we start with a 0. There are a lot of calculations we can do that are easier to do if we already start at 0. But that's again a topic that will come up quite a bit later. For now, you just have to consider that starting at 0 is less wasteful. And so we do that, rather than doing it the human-centric way of starting with a 1. Now let's have a look at a model of a computer, which starts, of course, with the memory. You can see this is a long sequence of memory cells. There are quite a bit more on the right to here. Just imagine them being there. And each cell has a fixed number of ones and zeros it can hold. To make our life a bit easier, I've decided to represent everything in decimal numbers. So the numbers you're used to, rather than binary. That also make things a bit more compact, which is quite nice for visual demonstrations like this. And each memory cell has, of course, an address starting at 0. And this could be the state of your working memory, the RAM in your PC. What do we do with this memory now? In a computer, we have this thing called CPU, the Central Processing Unit. And it's like an administrator for your computer. It keeps track of what has to be done, what has been done, where everyone is currently, what everyone is supposed to do. And this everyone is, for one, the memory itself, which is, in my opinion, the most important part. But it also has access to a couple of other different features of your computer, which you don't need to think about. It's just a lot of hardware that is used in clusters to make designing everything and understanding everything a bit easier. We don't get into CPU design, you don't need to understand that part. What you do need to understand is that this CPU considers this memory to be not just some numbers, but also a list of instructions. As I mentioned earlier, your memory contains everything. It could be anything. It could be just data. It could also be the program you want to run. And the CPU definitely considers everything in here first as instructions, as a program. As far as the CPU is concerned, everything in here is an instruction. There is no data. That's more a coincidence of the way we program things. And since everything is an instruction and everything is neatly arranged from 0 to 1 to 2, 3, 4, and so on, well, why not treat it as a list of instructions we have to progress through? Like a little to-do list. We start at 0 and then 1, 2, 3, 4. We just follow those instructions. And to keep track of that, we have this thing called program counter. It's another memory cell, but it's not really the same memory as this main memory we have up here. There's a very special place in your computer for something like the program counter, which has a very special meaning. And this special place is called the registers. There are several of them. And well, the actual number depends on your computer. In this case, we have 3 memory cells. We're going to learn about all of them today, that are combined into 3 registers. And the first one is the program counter, which always tells us which memory cell we're currently interested in. So which memory cell holds the instruction the CPU wants to perform first? Let's make a little marker in here. Think of it like a bookmark. That's where we want to start. And to actually give us something to practice on, let's load in an actual program. Give me a second. I haven't used this in a few days. Why is it now? Yeah, whatever. And there we go. So we get a few, I'm not interested in that. We have now a few different numbers, not just zeros. And as you can see, all decimal, not binary, makes it a bit more convenient for us. The computer operates roughly in 4 distinct steps. And the specifics how these steps work, well, the way the computer operates can be a bit weird if you include specialized hardware and optimization. I break it down into the following 4 steps. Please don't come after me because this is not a pure von Neumann cycle. And that's, by the way, the name you want to look for if you're interested in the specifics. Von Neumann. That's the guy who invented this style of computer. There are alternative ways the computer can be constructed, and there are computers that work based on different principles. They're just a lot less common. In our computer, we start with the first step, which is reading the operation. Operation is basically the instruction, but only the specific type of instruction. That doesn't make a lot of sense. That's because you're probably missing out on the second step, which we're gonna get to in a second. Read operations is just going to jump to wherever the program counter points to, and it treats that number as one specific operation. The computer knows a set list of existing operations. They are hardwired or potentially actually programmed into it. That's where we have stuff like microcode, but let's not get into that. Again, CPU design and everything gets a lot more complicated nowadays. In the good old days, this was not hard-coded. A 2 meant very specific thing. And for us, a 2 refers to the operation write accumulator. A write accumulator uses the memory and another register, the accumulator, which is bundled into a subsection of our CPU, the arithmetical logical unit. Think of it like the CPU is the administrator or the employee, someone that handles the actual tasks and organizes everything and follows the instruction. And the ALU is just the calculator they have on the side that does the actual calculations for them, figure stuff out. And the accumulator is essentially the display of your very simple calculator, what you can see in there. It holds a single value, and it's, again, separate from the main memory. Write to accumulator, that's what we call the operation, 2, takes a value from memory, so from anywhere in here, and copies that value into this register, the accumulator. The accumulator is a specific register, we know where that is, but we still need to figure out from where we want to copy the value. It could be anywhere in memory. How do we specify which memory cell we want to copy into the accumulator? That's where the next step comes in. After reading the operation, write to accumulator. Whoop, that was too fast, sorry. There we go. We're reading the operation. We go to the next step, reading the argument, by which I mean reading the additional information we need to perform the operation. Not every operation needs additional data, but a lot of them do, and in this computer at least, there are always addresses we want to work with, addresses in main memory. And the way the computer does it is it takes the value in the next memory cell over and assumes that is the additional data we need for our operation. That's the argument. So when we perform the second step, or repeated cycle, we're reading the address we want to use for our operation write to accumulator. Now address 6 is here, which is currently holding an 85. So now our next step, processing the operation. We're taking the value from memory cell 6 and copy that to the accumulator. Done. Operation is finished. But since we have a list of instructions, we need to, of course, now switch over to the next instruction. So the first instruction was this write to accumulator, which involved the memory cell address 0 and 1. These two combined made up this instruction we want to perform. 2 is the operation, 6 was the argument, some additional information for that operation, and combined they make up one instruction. This is where we get back to earlier, where sometimes you have individual cells and sometimes they belong together. This is one such case. One memory cell cannot hold enough information to tell the system that it wants to perform write to accumulator and which address to use. The address alone, in this case at least, will take up all the space available in one single memory cell. So we need 2 memory cells to store the instruction as a whole. To progress forward to the next instruction, we have to increase our program counter by the number of memory cells that were involved in our instruction that we just performed. We have 2 memory cells, so we have to increase by 2 to address 2. So now the program counter points at a 4, which is going to be our next operation. We just start all over. We finished 2.6, the first 2 memory cells, 1 instruction. We're now performing the second instruction. 4 is the operation add, and we're talking about a purely mathematical addition. We want to add 2 numbers. One of these numbers is what we already have in the accumulator. Essentially, we just typed in the number 85 in our calculator, and now we want to add a second number to that. So add is just like write to accumulator, an operation that requires additional data. So once we figured out it's add, we go to step 2 and read the address and the next memory cell over, 7. And we're going to use that information in our third step, in the processing. And we take the value in address 7, 170, and add that on top of whatever is already in the accumulator. Brings us to 255. And finally, we have to go to the next instruction. And once again, we use 2 memory cells for our current instruction, so we have to increase by 2, bringing our program counter to address 4. And this time the operation is read from accumulator. It's exactly the opposite of operation 2, write to accumulator. This time we take the value in the accumulator and copy that to somewhere in memory. And again, we have to take the value where we want to store the data from the next memory cell over, from the argument, address 8, which is here. Currently that contains a 0. But now when we perform the operation, we copy the 255 into address 8. And then we increment the program counter again, once more by 2. And we start the cycle over. Here's where things get funny. The computer assumes everything is an instruction, or at least an operation. Now we as the humans, we know this 85 is the value we used for the addition earlier. We combined that with 120, the next value in here, and generated a third value. These are just numbers, values we intended to add. Those are not operations, at least they weren't meant to be. The computer doesn't care. The computer doesn't have the concept of this is just data, ignore it. It sees a value in here, and it tries to interpret that value as an operation. That's what it's hardwired to do. It can't do anything else. But 85 doesn't exist as an operation. It doesn't know what that is. It cannot find any instructions on how to handle this. So it just breaks down. Of course, that's rather a naive way to handle things. And certainly you can implement specific error behavior for cases like this. Not just this, there are other errors that might happen in your CPU, and you can hardwire things or program things to circumvent these cases or have special handling for them. That all depends heavily on what exactly you're building or what machine you're programming on. For example, you could do something like, if a case like this happens, execute a very specific program that's somewhere else in memory. Just set your program counter to some other part, just jump ahead quite far to the end and execute that program, which might be something specific to inform the user something really bad happened. We don't need to go that far for our system. It's just, yeah, it's now frozen in place. Let's have a look at a different program. Let's load it in, start fresh. Looks pretty similar to the first one. At least you should recognize these three numbers in addresses 0, 2, and 4. Those are the very same operations. And these are again three instructions. But something interesting is different this time. I'm reading the operation first. It's a 2, so it's a write to accumulator. And then we read the address from where to copy the data. We want to copy from address 0. Address 0 is where our program counter is pointing at currently. It's the operation 2. We want to copy the value from this memory cell, the 2, into the accumulator. It's the opposite of the earlier case, where the computer tried to use a data value as an operation, which didn't work. Now it tries to use an operation as a data value, which does work, since it's just a number, and of course it can copy the content of this memory cell into this memory cell. No issue. It's a bit weird to us as a human, but why not? It works. There's no conflict of interest here for the computer. with that instruction done, we go to the next one, add the 4. We read the argument in the next cell over, which is this time 2. So once again, we're using the operation itself as a data value. And we're adding this 4 to the accumulator, giving us 6. And now it comes the weirdest one of them all. Read from accumulator, opcode 1. Reads from the accumulator and writes to address 4. Well, address 4 is again our program counter. That's where our operation currently is. We want to write into our operation. And the computer doesn't care. As far as the computer is concerned, once we have read the data, that memory cell is free for use. Whatever you else want to do with that. Now it just contains the value 6. Doesn't bother the computer anymore. We just jump ahead to the next instruction. The next instruction is 0, which is a very special operation actually. It does exist, it's an actual valid operation. And unlike the previous examples, this operation doesn't require any arguments. So we can basically skip this next step. And the special thing about this operation is that it's not doing anything. So we can also skip the third step and just execute the last step. We increment the program counter. This time, however, we only increase it by 1, since we only use this one memory cell for our instruction. Go to 7, and then we execute that. Nothing happens, nothing happens, nothing happens. And we can continue this throughout the entire piece of memory. 0 is also called the no operation NOP. It's quite common operation in basically every computer. And an operation that does nothing might seem wasteful at first, like what's the point if it's not doing anything? But there's a point to them. They do have some uses. They're convenient to have. But those situations are admittedly usually a bit of a waste themselves. Like, I'd argue that if you really write a program correctly and really want to optimize every last bit out of it, you will not have any knobs. But that's very hard to do. And we'll see how that looks in the far future. Now, just to demonstrate something else this computer has, at some point the memory will end. And for this computer, that is memory cell 255. That's how big our memory is. We have 256 memory cells. Keep in mind, we start to count at 0. So this is not 255 memory cells. This is 256 memory cells. The last address is 255. Again, +1, -1, you always have to keep that stuff in mind. When we want to increment now the program counter to the next operation, we have a bit of an issue because there is no next address we can go to. Similar to earlier, when the computer just doesn't have any idea how to progress, it will just stop. Though this time it's not an error, it's just, yeah, finished. Our list of instructions is done. The computer has completed all its tasks and will just shut down. Again, different hardware might solve this differently. It might just jump back to the very first address and just repeat the entire program. Different things on different hardware with different programs. if we assume that I always jump ahead by 2 or 1 space, these instructions take 2 spaces, and these knobs take always 1. We always move forward, so at some point this computer will always stop. If I put everything just to 0, it will just take 256 operations, but it will take at most 256 operations, and then we reach the end and the computer will not do anything anymore. We can prevent that from happening. See, just like we use this register to store values, to manipulate data in here, to write data into, to read data from, we can also manipulate this register. And you might imagine that the program counter is a bit protected, but it's not really, for good reason. Let me load another program. We start with the first operation, and to make things a bit easier for all of us, let's add this. Just shows you what the number actually means. A little shortcut for what operations we're looking at. Number 2, again, write to accumulator. Second step, we'll read the address, which we're also going to show here. And we read from address 6, this 3, copy that to the accumulator. Easy enough. Now comes a new operation. 5. 5 is subtraction. Just like the addition, we subtract a value from another value. Specifically, we subtract a value from a memory cell, now 7, from the value in the accumulator. In address 7, we have a 1. So we subtract 1 from 3, which gives us 2. All right. Operation 8. Now things get interesting. 8 is an operation called jump. And as the name suggests, it lets us jump in our memory, in our flow of instructions. It also takes another argument. This is 2. That's the address we use. And guess what happens? Three, 2, 1. We didn't read the value from address 2, we jumped to address 2. So if we go back, program counter was before at address 4. We execute the jump instruction, which copies the value we have in the next memory cell, the argument, the operation address, into the program counter directly. Which means the program counter now points at this address 2, where we executed our subtraction earlier. And also because we already changed the program counter, jump is special in that the last step is skipped. There's no need to change the program counter since we already did that. So we start all over with reading the operation, subtraction, just like earlier. We subtract the value at address 7, the 1, from our accumulator, 2. All right, that's a 1. Next instruction, jump to address 2. And next operation, 5, we subtract. the value from the value in address 7 from our accumulator. So 1 minus 1 is 0. Next instruction, we jump to address 2. Next instruction, we subtract the value in address 7 from the accumulator. So we subtract 1 from 0. Now here's something interesting. We subtract 1 from 0, which is minus 1. Can our computer actually handle negative numbers? The answer is no. I mean, it can in a way, but that is up to the programmer. The computer itself, the hardware on its own, doesn't understand the concept of negative numbers, but they don't exist. Let's quickly go back to the drawing board, so to speak. If we look at earlier, our memory was separated into chunks, but it is just one continuous list of zeros and ones. We don't have any dash in there to indicate a negative value, but it can only express values as ones and zeros. So for a memory cell, let's make it simple. With 3 digits, we have a limited number of values we can represent, or a limited number of different combinations of values we can have. I'm writing them all down right now. And that's it. These 8 different combinations are all we can do. That's all we can store in this memory cell. And if we decide that this is 0, 1, 2, 3, 4, 5, 6, 7, well, there is no more negative values. There's also no values above 7, not just not below 0. A memory cell has very clearly defined limits on what data you can put in there. So when we try to add to this or subtract from this, what you will see as the end user is this. The whole thing ends up as a ring and not a linear list. We can add 1 continuously, but we always end up back in the beginning. And we can subtract 1, of course, but then we'll just start again. If you imagine the normal list, there's a pattern to this, the way the numbers increase. This is very simple binary. By adding 1, this is the pattern that we would see. And once we have filled all these 3s, well, if you imagine that we have a 0 in front of here, the next logical number would be this. So in a way, adding 1 down at the 7, for example, we do get a new number, but because our memory cell has a limit to how many digits we have in there, we don't see the additional numbers. We only see the numbers in here, this combination of 3 digits. So as far as we can tell, we just go back to the beginning up here. We're going around the circle, back to the beginning. That's an overflow. And the reverse, when we go from 0 down to the 111 to 7, that's an underflow. And when we go back to the system, this has to do with the way... Why is it... Okay, technology. There we go. That's the underflow. With the way we represent negative numbers, or the way we use negative numbers in binary, usually, what we would expect with this format with 4 digits would be that. Don't think about how this actually works. That's a topic for another time. But you can look it up. If you're interested, look for 2's complement. Specifically 2's complement. That's the common representation. But yeah. Our memory, limited to only 3 digits, will only give you a limited view of the numbers. So in theory, you won't get the same number again. There's no over or underflow. But because our memory is limited in size, you only get to see a small part of those numbers, of those infinite amount of numbers. And so as far as we are concerned, it's all just a ring, just a circle. We always go in one direction along the circle, and so we constantly hit the same numbers again and again and again. For 8 digits, for 8 binary digits, or as we would call them, 8 bits, which is what I use in this CPU here, the underflow would bring us all the way back to 255. And something you also can notice here, if you look at this little circle, it's now filled. This is a little flag that is set in the ALU that tells us that an underflow happened. We jumped from 0 to 255. It would also set this flag whenever we have an overflow and go from 255, for example, to 0. It's a simple mechanism in the background that can be used in very special operations to help us identify these happening. And so we can write programs that react to an overflow or underflow happening. Otherwise, we might not be aware of it. As soon as I do the next operation, well, next time we make a subtraction, the flag will get reset. Let's first make the jump instruction once more. Jump back to address 2. We perform the subtraction. Subtract 1 from 255. But that operation itself has no under or overflow. 255 minus 1 is just 254. So the flag gets cleared again. But that is an important distinction. We do have a way to notice overflow or underflows happening. We can't just quite tell the extent. But in this way, this whole thing will just cycle through these 2 instructions, constantly subtracting 1, counting down from 255 to 0, and then starting at 255 again, counting down to 0 once more. Eternally. This program will never end. We'll never reach the end of the memory, we never get any errors, that would break the system. From now on until the moment we decide to shut down the PC manually, it will just keep running. That is something you can do with the jump instruction. Usually, of course, you want to do something a bit smarter. But maybe you actually do want to just constantly count down a number. Let's try to make this whole thing a bit smarter. I'm gonna keep the program for the most part. I'm just gonna add one operation after the subtraction. So we had here the 5 for the subtraction and the 8 for jump. Now pay attention what happens. Suddenly we have a 9 in here coming as the next instruction. Let's see what's going on here. So first we write the 3 to the accumulator, like before. We subtract 1, this time it's an address 9, from the accumulator, sure. But now comes a special operation, and it's another jump instruction. But not just jump, it's jump if 0. It's a conditional jump. A jump would simply take whatever address we load, here it's a 10, and copy that into the program counter. Jump if 0 has 2 possible outcomes. It can copy the data directly into the program counter, so it could set our program counter to 10, but it will only do so if and only if the accumulator is exactly 0. Jump if 0. Our accumulator contains the number 2, which isn't 0, so our jump instruction will do nothing. And we just go to the next instruction, which is our jump from earlier, which will straight up jump to the subtraction again. We subtract 1, and we make another jump of 0. 1 isn't 0, so we ignore this operation, go to the next one, jump, we go back to subtraction, and now the accumulator is exactly 0. So we perform the jump, bringing us this time forward onto address 10. After the pure jump instruction and after all our data values, 3 and 1. So now this computer will just continue to run this entire memory, which is all zeros, until it hits a stop. So the jump instruction can cause the program to divert in 2 different ways. Jump F0 has caused a branch to appear in our program flow. Depending on how our program calculated data before, how it arranged the data and presented it in the accumulator, we will now basically choose between 2 different programs. One program is going to just continue as is in ignoring this operation, which means we go to the jump instruction, which will cause the eternal loop from earlier. But it can also decide to run a different program, which starts at address 10. We branch off in 2 different directions. We can change the behavior of our program during the runtime, or we can trigger something in the beginning that will cause it to divert into a different behavior later on. This is an incredibly important feature. Being able to cause our program flow to divert based on conditions that change during runtime. It's one of the reasons computation is possible. Otherwise, we would have just a simple calculator, nothing more. Like a fancy calculator, sure, but just a calculator. But because we have this ability to branch off, to cause two different programs to execute with just one simple operation, we can cause the program to, for lack of better terms, think, to make decisions. To show different behaviors in different scenarios with different data, and to treat it differently. Of course, that doesn't help if the program is predetermined. The computer is deterministic, so this program, regardless of how many times I restart it, will always end up doing the exact same thing, despite having a branch operation. Which kind of defeats the purpose, you might say, of the jump if zero instruction. It is still useful, because it makes certain computations possible, or calculations, but you're right, on its own, this doesn't help us too much. Let's introduce some new operations. This is going to be a new program. We start with reading the first operation, 11, which is read IO. It is the counterpart to read accumulator, only it's not targeting the accumulator register, it's targeting the IO register. If the program would always execute the same way, there is no point in running the program multiple times. Once you've run it the first time, you have all your results and there's nothing new to discover. But if you have an IO register or any other capability of interacting with the outside world, you have suddenly this unknown that can influence the program while it is running. It can change the behavior of the program, it can change the outcome. So even though it's one single program we defined and wrote into memory, it can do different things now thanks to this input-output register. The way it works in this specific hardware is that we have this one special memory cell, a register, that can be seen from the outside, so we can read the data that's presented in here, and it allows us to give data into the PC. So the PC can read from here, but we can manipulate that data directly from the outside while the program is running, but we can also see the data that's presented here if the computer wants to show us something. And read IO specifically will start by reading data from the input-output register. So it expects us to provide data now. And let's see. What do we use? What do we use? Oh yeah, let's do an 8. And we're doing a second operation. Read input output. Again, it expects us to put a number, and this time we're gonna use 4. This is gonna be good. Now, just like read accumulator, it takes the value from the register and puts it into the memory, in case you didn't notice already. Should have mentioned that earlier. So our 8 and 4 were input into the addresses 12 and 13. That's the input we presented in the start. And next operation is write accumulator. Actually, the next 3 instructions should be very familiar. We read the data from address 12, which is the number we've input in the beginning. Put it in the accumulator. Then we add to that the value from address 13, which is the second number we've input while the program was running. We get a 12. And then we read accumulator, write that data into address 14. And then we close off with operation 12, which is another I/O operation. This time it's outputting the data, write I/O. So we take the value in address 14, our sum, the 12, write that to the I/O register, and also send out a signal that there is new data to be read. So with the I/O register, we can have the same program calculate different things depending on whatever we've input while the program is running. You have to imagine that while I have it quite easy in here, changing these programs in a real computer, this is all hardware, just pure hardware, some memory chips somewhere, some flip-flops, flash drives, whatever you have that stores the data. Directly changing that is difficult, especially if you want to change everything in one go. Having a special I/O register, which is just one piece of very special memory that can be hooked up to some input, some switches maybe, some LEDs for a very, very simple input. Yeah, that gives you the ability to interact with your program without constantly need to reset everything and load in completely new data, which might be complicated depending on what memory you have. But there's a bit more to this. See, what happens next is we increment the program counter, pointing us to the next operation. And this is exactly the situation we had in our first program. The computer tries to interpret the value in address 12 as an instruction, as an operation specifically. But this 8 was input as a data value. It's not an instruction. Well, it doesn't really matter. It still tries to interpret it, and it just happens to be that 8 is actually an operation it knows. It's the jump instruction from earlier. So we process the jump instruction, which reads the second value we've input as the address. And so it performs a jump operation to address 4. Which means we write the accumulator. And we add a 4, and we read from accumulator. And then we output the sum. And we jump back and repeat the whole thing. And we've caused another infinite loop. This time, however, not because it's in the program itself, but because the values we provided accidentally were executed as code. We load the program and do something less fitting, sorry. Let's do say 5. Let's recreate the first program. is it not? Numlock. Like that. Sum them up. Store the sum. Output the result. And now when we try to execute it, we're hitting the exact same issue from our first program. 85, the data value cannot be interpreted as an operation, so we stop. But yeah, by doing it like this with a jump instruction, we can cause different behavior to happen. We'll also do this, which causes it to add 8 and 0, which, well, cool, that's an 8, but it also causes the whole thing to just completely restart the program. So we can actually create a program that lets us input a new program in a way into the input-output registers. We can configure a program in here that doesn't change, that lets us rewrite the memory in here according to instructions that are provided during runtime. We can provide a completely new program in theory that's provided through the I/O register when we start the program. Now, in this case, it might be a bit more malicious because that's not what this program is intended to be, but you could write this program to specifically read the data and intentionally write that data out as program code to be executed. You could write a program that has the intention to read a program during runtime to execute. You might call something like that a bootloader. For example, it's quite common actually, that type of program. You're using it all the time. When you start your computer, it will first execute. I mean, there are a lot of safety stuff, and nowadays computers are a lot more robust in that sense, but in theory, you have a simple program that does nothing more than read in data from somewhere. In that case, though, not from you as the user, but from the hard drive, and writes that out into the main memory as program to be executed. That is your operating system. And your operating system itself will then also load data from somewhere, again, usually your hard drive, write that into main memory and execute that as program, like the browser you're probably having open right now. So it's quite common that during the runtime of a program, you're writing a new program into memory to be executed. That's actually quite intentional design. It's just, it can also be done maliciously, and that's why there are a lot of safeties in computers that prevent you from just randomly writing stuff into memory. It's a good thing. That's a very good thing. Though it can be frustrating sometimes when you write a C program which doesn't really prevent you internally from addressing addresses you should not be addressing, and then you get a nice segfault error. Not that it ever happened to me, because I'm a good programmer and I never make mistakes with my pointers. Plus nowadays I use C#, so I rarely have to use pointers anyway, but point is, we can read data while the program is running, and we can do some really cool stuff with that, from just having a simple calculator to writing a completely new program. And I think at this point we're gonna stop for today, because I don't want to put the upcoming topic in the end of our last 15 minutes, when I prefer to talk about that for half an hour next time. Or maybe 45 minutes. And with that short with that short introduction, we're done with the basics of how a computer works. And we're gonna progress from here into how we actually program a computer. With that, I wish you a very nice Sunday evening, or whatever else you have currently, depending on your time zone. And I'll see you next time.